My name's Szumski, and this is my colleague, Mark Goddard.
Hi.
And we're from Cray. We work in the centre of Bristol, so we're pretty close. And we're here to talk about Diskful and diskless deployment at Cray. First of all, Cray are basing their next generation system management software on OpenStack, so that's why we're here. And a typical Cray machine, it consists of large numbers of diskless compute nodes and a smaller number of Diskful service nodes. So the focus of this talk is really about deploying those nodes, both the diskless and the Diskful ones, in both cases on bare metal. And we'll finish off with a talk about how we test this. Just to give you an idea of the scale of these machines, a typical XC series compute blade consists of about 4 nodes per blade. You can have about 48 blades per cabinet, and the system scaled to hundreds of cabinets. So you can end up with tens of thousands of nodes. And our diskless driver, which we're hoping to use for booting systems like this in the future, is currently based on an implementation of Satoru Moriya's spec called the Volume Connected Information for Ironic, which was recently approved. But we've kept this fairly simple at the moment, so we haven't made any changes to the database or any OpenStack APIs.
Ignorant question, are these x86 systems or something else?
Yeah, these are x86, yeah. Although we have worked on ARM systems as well.
I thought it was ignorant.
Yeah, so this diskless driver, in order to help with scalability, it supports read-only multi-attach with overlay file system. And we've made our driver available. It's not merged into the OpenStack code base, but if anyone's interested in looking at it, you can follow this link. This is a technical explanation of the flow of how this works throughout the various OpenStack services for a diskless boot. And the whole thing starts when you invoke Nova boot from the Nova command line. And you specify a cinder volume as part of that command line argument. And that command, it trickles down through Nova, through the API, until it gets to Nova compute. And at that stage, Nova compute, it reserves an IP address for the ironic node from Neutron. And then the next thing it has to do is to give the information that the ironic node needs to connect to the cinder volume to the ironic node. The first thing it does is it looks up the IP address of the ironic node on the storage network, or the MAC address. And in the case of the MAC address, it will look up the IP from Neutron. And then Nova, it calls Cinder and tells Cinder to prepare the block device for the ironic node to connect to. And Cinder comes back with some connector information. And Nova then updates ironic with that information, so the node can use that to connect to the Cinder volume. So at that stage, the ironic vert driver calls the ironic API, and deployment begins. Deployment starts by first caching the images required to boot the ironic node. So you've got the kernel, the RAM disk, and it also generates the PXE configuration file, which contains the kernel command line. And on that kernel command line, you have the details of the iSCSI target the ironic node should connect to. Also, around about the same time, TFTP is configured to serve those images up to the node, and Neutron is configured to respond to DHCP requests. So at that stage, Ironic then configures the node to boot using PXE, and it turns the node on. And the node turns on, it broadcasts, and it gets a DHCP lease from Neutron, and also the location of the PXE bootloader. and the other information it needs to boot. The ironic node, it then TFTPs across the kernel and the RAM disk, and then boots the kernel, boots the RAM disk, and the last thing it does in the RAM disk is mount the iSCSI target and then pivots into that root file system. And at that stage, the ironic node is booting from the Cinder volume that you specified on the command line. Now moving on to Diskful deployment, I just wanted to give a couple of example products that use this at the moment. And the first of these, we started off with the smaller products rather than the big machines in the beginning. The first of these is called eLogin. And eLogin, it's an external login server for the Cray X series machines. And this provides the ability for users to submit jobs to the machines. It provides a development environment with the Cray compiler that they can use to compile their jobs. And it runs independently of the XE machine, so you can do all of this stuff regardless of the state of that machine. And there's a little diagram here. The actual machine running OpenStack here is the Cray management server shown in blue, and this provisions these eLogin nodes, which are shown on green on the right side of the diagram. And these eLogin nodes, they're Diskful, and the image that you have to deploy is fairly large, maybe of the order of 10 gigabytes. So we've hit some of our first scalability problems when you're trying to boot quite a few of these. And I'm sure Mark can tell you about that later if we get to it. This is another Cray machine which uses Diskful deployment, and I believe that we shipped the first one of these fairly recently, or at least in the near future. And this is the Urika-GX analytics platform. This is like a big data analytics machine. And a typical one of these, it consists of a single cabinet, up to 48 blades. About 44 of those are Diskful compute nodes. And each one of those Diskful compute nodes, it has a local hard disk and an SSD. And we use OpenStack to deploy this software stack on the right, which contains things like the Cray graph engine, Hadoop, Spark, to those Diskful nodes in the cabinet. In order to do the Diskful deployment, Cray uses the Bareon agent. The Bareon agent was originally part of the Fuel project, which I believe was initiated by Mirantis. And the Bareon project is really about operating system installation. And out of the Bareon project, we just use the Bareon agent with Ironic. And this is an out-of-tree project, and you have to apply it as a patch to Ironic. What do we require from Bareon? Cray has some perhaps non-cloud-like use cases. And so we do things like we deploy multiple images to nodes so we can switch between different operating systems. We like to be able to use rsync to make deployments. So if we want to verify an existing deployment, or we want to upgrade an existing deployment without transferring the entire image, we can make use of rsync for that. And we also typically have complex partitioning schemes which might include LVM and various other things. This is an overview of how the Bareon agent works. And at first this looks like a bit of a rat's nest, but it's not too different to the diskless boot in the first half. You can initiate the process by calling nova boot again, and you specify the operating system image that you wish to deploy as an argument to nova boot, along with a deploy config which defines the partition schema that you want on the node. And this can be fairly complex in many cases. And it can include information like rsync flags that you wish to use, whether you want to do a verification delete files which shouldn't be there and that type of thing. At the same time, you can pass through a list of driver actions. So typical actions that you might like to do could be to copy an SSH key over to a certain partition, or perhaps update the firmware on the node. Once you initiated that command, in a similar way to before, Ironic pixie boots the target node, and it pixie boots a RAM disk which contains the Bareon agent. And this RAM disk is based on a CentOS minimal distribution, contains Python. Bareon agent is written in Python. While this image is booting up, Ironic just sits there and waits for this to call back. So once the node is booted, it calls back to Ironic to tell it that it's ready, and then the process is really driven from Ironic after there. The Bareon agent, it executes the provision script that you supplied in the beginning, the deploy config, and it will copy across the images that you've specified in that script, and you may have more images which are specified in that schema in addition to the image supplied on the command line. After that, it runs the deployment actions, such as here it's changing the BIOS. And then it reboots the node, and the node boots from the local disk, and your image loads up. So I just did a quick comparison of the Bareon agent with the Ironic Python agent that some of you might be familiar with. The Ironic Python agent is a similar concept, which is part of OpenStack officially. I thought it would be interesting to just quickly cover some of the parts which were missing from the Ironic Python agent, which led us down this path with Bareon. And I guess the first thing to point out is that when we made the decision to use Bareon, both of these projects were fairly young. So the picture you see here isn't quite how it was in the beginning. But you can see that both of these agents have things in common. They can both be used to clean partitions and disks which are on the node. They both support QCOW images. They can both be used to perform deploy actions, so for example, firmware upgrades. They can both provision partial images, partition images. IPA can write whole disk images. We don't have a use case for that at the moment. And there are a few things that Bareon doesn't support which could be nice, like logging of metrics. And on the other hand, Bareon it supports LVM and this multi-boot feature where we can boot two operating systems. And most importantly for us, it supports rsync. And I think that some of those features, if you follow the various discussions, I put a couple of links, they're considered to be outside the scope of Ironic. So perhaps the hope for getting those into the IPA agent is fairly low. I'll now hand over to Mark Goddard, who's going to talk about testing.
Thanks, Doug. So first off, little disclaimer. I'm not a full-time tester. I'm a software developer. But I have spent quite a bit of time testing our management stack and working with it, writing tests, and getting involved with the infrastructure as well. So what I'd like to cover is a bit about our production environment. Doug's already covered some of that, but I'll go over it again, perhaps from a testing viewpoint. Some of the challenges that we face when trying to test these systems. Our current solution, some of the issues that we have with it, and then some of the things that we're looking at doing in the future. So, very simplified, of course, but at a very high level, what we have is a small cluster of management nodes, which we've termed Cray management controllers, CMCs. We've got a set of managed nodes, which, as you can tell from their different colorings, may be of different types. perhaps some are diskless, some are Diskful, and perhaps they're just as different as having different sort of flavors in the Nova lingo. We connect them up with a management network and often various other networks of different kinds. Typically Ethernet, but on the higher end machines we have more exotic networks as well. So just a little bit about what these nodes look like. The CMCs, Cray management controllers, are generally sort of fat x86 nodes. We use a CentOS OS. We lay down a set of Yum repositories on top of that, install them via an ISO image. We then have a set of Ansible plays to install and configure our software stack on top of the OS. We deploy the services in Docker containers, coming soon. At least some of them are coming soon. We've already implemented about half. We're working our way through them. The managed nodes are in general bare metal, although we are looking in the future to supporting both VMs and containers for different use cases. And they might be Diskful or diskless nodes. We deploy them via Nova and Ironic. Some of the challenges we face are that Cray machines are very big. Doug mentioned the size of some of the big ones. We can get to tens or in some cases even hundreds of thousands of nodes in a single machine. It really is quite big, hard to test. They're also very expensive. I can't afford one. And Cray itself can't even afford some of the biggest ones just for R&D. So we can afford some of the smaller ones. Perhaps we can afford a rack or two, but a lot of the development at the really high end of scale is done through simulation and testing on customer machines, which they are very grateful for. We could double the price and buy one ourselves, but they're not very keen on that. The bare metal environments that we run in are quite inflexible. We're all used to the Nova API here, where you can spin up a VM of whatever size you like and don't really care where it is, or you can connect it up to anything you like. But actually, bare metal machines are real things in a real place, connected up with a fixed number of physical connections. There are things you can do in the network to make things look different, to change the topology, but that only goes so far. So, virtual machines to the rescue. We use Vagrant as an abstraction layer to abstract away the different providers of virtual machine. So on our Linux servers, we typically use libvirt and KVM. For those of us who are blessed with Windows laptops, we usually use VirtualBox. One of the great things about Vagrant is that we can use snapshotting to grab a copy of the disk at various stages of deployment. So I'll talk a bit about how that gets used, but at a high level, it's used for sort of a pipeline of jobs in CI, and also for developers to be able to pick up a snapshot of an installed system. The Cray management controllers, the virtualized nodes that we use for testing, consist of a CentOS base box. We then run through the standard automation, the standard installation process with some automation scripts around it. We have a concept of provision plugins. I'm not sure whether we stole that from Vagrant or not. It's certainly integrated into the flow of bringing up a VM. Essentially, it's a set of shell scripts, and we can specify an arbitrary pipeline of these shell scripts to run in order to set up the VM. The managed nodes, once we've got a management plane, we can deploy them via Nova or Ironic. Well, sorry, Nova with Ironic underneath. So one reason why this is the flexibility of this is good is that we can integrate it into our continuous integration pipeline. So we can have various jobs running at the same time on a handful of servers, spinning up VMs with fairly flexible different environments for testing. So a very simple view of the pipeline is that we build our software ISO containing the Yum repositories of our software stack. That gets archived off. We then pull that down, spin up a new environment for testing using Vagrant, install the management stack on top of it from the ISO, run through the Ansible scripts, and once that succeeds, we run through a set of test suites to validate the software stack. So we've got a few different tests. Some of them involve deploying reference stacks, things that look a bit like the products that Doug mentioned earlier, so eLogin and Eureka. We run Tempest. We do have some issues with Tempest, partly because it's a bare metal cloud and can't do everything that a virtual cloud can do. So we had a long battle with Tempest trying to work out which failures were our fault and which were not expected to work at all. And we also got a suite of homegrown tests, and these capture our specific use cases. I'll leave you to work out what this is trying to say. So the issues that we had with testing, resource contention in our CI environment. We got some fairly fat nodes running CI, but even so, spinning up VMs is quite memory intensive when you've got perhaps a few jobs running on a node, each of them running one or more management controller nodes, which are quite big, and perhaps a few other managed nodes. The monitoring and log aggregation stacks that we have alongside OpenStack are also quite memory intensive. Have to resist the temptation to just turn them off for testing purposes. There's a lot of I/O activity, which I think is really what stings. It's things like package installation, copying around ISOs from place to place, both installing repositories into place and then installing the packages from those repositories. Perhaps there are things we could do to tune the I/O there, but well, also there's the deployment of the managed nodes. So Doug mentioned 10 gigabyte images earlier. We don't test with images that big, but there's still a handful of gigabytes, and when deploying many at one time, it can really churn through the I/O. Another problem that's bitten us is that the Vagrant libvirt provider is buggy, and we've got a few patches for that. But even so, I think we still find occasional Ruby tracebacks, and no one wants to admit to knowing enough Ruby to to fix it, because then they're labeled as the Ruby developer. Scalability is a tricky one. So we've got a multi-node Jenkins setup with a single master, multiple slaves. But at the moment, our testing environment is limited to a single node, so as many VMs as we can pack onto that node. So clearly, at some point, we're not going to be able to simulate a Cray in a single node. So. Things that we like to do in the future. I think the first issue that well, probably the most pressing issue at the moment for us is that VMs aren't the same as bare metal. There are issues that we hit when installing to bare metal, which is the way that our customers install our management plane, that we just don't see in VMs. And having a test infrastructure that doesn't pick up those issues can really be problematic. So, with each release, we still need to go through some amount of bare metal testing. At the moment, that's mostly manual, but we're getting to the point where we can automate that. So, trying to use the same ideas as we have in our virtual environment, but deploying images to bare metal servers rather than the virtual machines. Clearly, that uses up a lot more resources, so we need a fairly constrained set of tests to run against that environment. Another thing that's been talked about for a little while now is OOO for testing. So one way of beating the scalability issues of our current setup is to replace Vagrant with an OpenStack cloud. So instead of spinning up VMs using Vagrant, we would use OpenStack and benefit from the scalability that OpenStack has. There are some good and bad points to that. I guess to some extent we're eating our own dog food. We're becoming more knowledgeable about the system that we're building, although it wouldn't be quite the same as the system that we sell. But the complexity could bite us. I think we all know that OpenStack can be difficult to operate. I think we've seen some talks that have alluded to that at points. And adding something like that into our testing environment may have its challenges. We have a proof of concept for this. So we use a heat stack to describe our test environment and let heat do the magic, and run our test scripts against the resulting stack. Another thing that we've talked about is everyone's favorite OpenStack card trick, adding another layer of abstraction. So what we would do here is wrap up Vagrant, OOO, and bare metal resources behind a single interface. So what that interface might look like, we're not quite sure yet. Perhaps a Python API, perhaps a service, but essentially a way of writing tests and automation against a single API, and have that potentially backed by various different things. So people running development on their laptops might be using Vagrant. Perhaps we would have CI jobs running against a OOO cloud, and then perhaps some of our other CI jobs would be running against bare metal systems. And perhaps those systems might be actual Cray products that look exactly like the things we're trying to sell. So that's all I've got to say on testing today. Does anyone have any questions?
Mark, you didn't mention Rally.
I didn't. No, we do run Rally. We don't do a lot with it at the moment, but we're starting to. So, good question. He's not a plant. Oh. So we do have a system. The biggest test system we have is a diskless 128 node system, and we're running a Rally on that at the moment. It's still sort of the proof of concept stage, but we are using it to benchmark deployment of those nodes, and also to benchmark our monitoring stack, which incidentally is based on Monasca.
How much effort have you invested, and how long has it taken to get to this point?
So we started this project about 2 years ago now. And it's grown a lot since then. So in the early days, it was a handful of people building a proof of concept on time borrowed from other projects. About a year ago, it started to pick up, but I think the time was still split, and really it's in the last sort of 9 months when it's really become a full project with a decent number of developers behind it.
And are you actually able to show a clear value in the testing that you're doing in terms of value back to the business? Is testing now something that's kind of weird? It's like, I understand why we do testing, or are you still struggling to say we need to do testing?
I think it varies person to person. Testing can be quite a time hog if you really fill in the pyramid. Writing unit tests is very time intensive, and the testing that I'm talking about here, the more sort of integration level testing, has its own challenges. So it can be hard to convince people that it's worthwhile. But I think when you have a good example of something that gets caught by the CI system that would just have gone out the door unchecked, probably unseen through manual testing or through, or even no testing if that's an alternative, I think people do start to see the worth in it. Do you struggle with that?
I think a little bit. I think it's difficult to put the right metrics around it to present it back favourably to the business. I think it's a journey that we're just starting on, so this is really interesting to see. But yeah, I think we do struggle with it a bit.
Part of the problem is that the closer to the developer that you've got the testing, which is where you want it to be to reduce the cost of finding errors, the less visible it is to the rest of the organisation. So what you say there, Mark, is fine, but obviously if you catch it and nobody who's paying the bill sees it, it's not, it's one of those things that is a no-win situation. You can only do
That's it. Well, it's kind of the post-analysis, isn't it? It's being able to say this was caught, and actually the knock-on implications of this would have been X on the bottom line to the business in terms of recovering from that failure. And that's the bit that I think can be very difficult to explain.
I think the great thing about, well, one of the attributes of Cray, though, is that, or a place like Cray, is that they spend a lot of time when you're building these machines doing verification work. So verification as a first-class objective, as it were, is in it, so it's really fantastic.
Well, that's something I kind of found a little bit strange. I would imagine that because these machines are so unique, bespoke, and one-off, that you would probably go through a full suite of testing before you got to customer deployment, right? So you would actually have the system to test. Or was that not the case? I mean, I can't assume the deployment model for a Cray system. So wouldn't you have it in your labs before you roll it out to the customer, or is it normally going right straight to the customer and you say, stop, hold on.
So it depends. I think each system is subtly different. They're expensive enough that they can be slightly tweaked and tuned based on the customer's demands. So we're not sort of rolling out identical appliances, and that can make testing difficult. So I think something we can do is, as machines are being built up on the factory floor, we do get access to them to run tests against them. But really, if you're failing tests at that point, it's too late.
Often I can imagine it's difficult to get the test engineers out to the manufacturing floor. So that's a big, in my opinion, big disconnect. You usually have the test engineers in one location. And I don't think
No, yeah, that's true.
Don't you think, though, that there's a degree to which the more you pay for something, the worse the quality is? The more, I'm not going to get quoted backwards and forwards, but the more bespoke something is, and the
in the way of fault injection?
Well, it's something we're really beginning to think about. So I think having that final point about having a single API or interface behind which you can manipulate the underlying infrastructure from under the sort of the feet of the infrastructure under test. That's one way of starting out, but it doesn't really answer the problem fully. In a virtual environment, you can do quite a lot. You can bring network links up and down. If you're in a bare metal environment, it gets a bit more tricky. You have to start talking to network switches, which is always problematic, but it can be done. Remote power management, you can pull plugs on things, but yeah, it's difficult.
The other question was probably when a test fails, especially in the virtual environment, you've got logs about 30 different machines, one of which will cause a problem you don't have a clue where, so they'll get attached to material somewhere. Have you done any work or any work on better basically in that tooling to debug cross machine systems without entering test runs? That's the enemy of my life.
We have a log aggregation stack, ELK. All of our logs will get piped into that. We're still really building up the tooling around analysis. So we've just about got to the point where everything's being aggregated into that stack. But the real hard problem is making sense of it, right? You've got the data there, but what do you do with it? And we're just starting to answer those questions. There's a team in the US that we work with that are looking into that at the moment. Sorry, bad answer, but
One of the things I'm actually experimenting with is actually not just capturing the log, but snapshotting the metrics all the time as well. Publishing more state casual metrics if you debug that.
we have a monitoring stack with Manaska, so we can use that, but I wouldn't say that we're using it in our testing at the moment. But
There is a Python project we started about a year ago to pick up where log aggregation leaves off and somehow structure the logs on multiple nodes in such a way that you can follow the transactions across nodes. Guy who's at Cluster HQ is coming in, so
We use Cray, very people with that correlation.
Are you really going to provision the compute nodes of the big cluster with this? I mean, we're talking about tens of thousands of nodes, and the customer wants to, a job's just starting out, a whole machine job's starting out, and you want some new operating system on the compute nodes. You've got 5 minutes tops. Really?
that is one of the challenges that we have, I think. OpenStack, as a cloud management system, is very good at handling requests that are spaced out in time from different users, and perhaps, I spin up 10 VMs, 5 VMs, 3 VMs, 2 VMs, but
HPC is a continuous denial of service attack.
you're right, it is, yeah, and I think that's going to be one of the most difficult things, and things that HPC is typically used to overcome that, like batching up of requests, are just don't really exist in the REST world. So it is definitely a challenge, but we're not at the point where we need to do that yet. I think we'll.
Are you not considering this for the provisioning of the management nodes, and then something special purpose for the compute nodes? That would make sense.
So, with Ironic and Neutron as well, you can. It's easy, and in fact we've done it to write a driver that will outsource any requests to something else. So perhaps if you've got a scalable supercomputing management system, for instance, then you can forward any requests to deploy a node to that. And the same again with Neutron then. If it's just forming an API with a driver underneath that forwards any requests to whatever your network provider is, then that, I think, is the answer, rather than trying to do everything within OpenStack. You still hit the limit. Can you get everything into the API fast enough? But
I guess it depends with what frequency you would reimage all the compute nodes. Right? If you're doing that every run or every set of jobs, that's going to become a very expensive performance bottleneck. But if you're doing it infrequently, and if you're able to stage it, stagger it over time, then you work fine.
Yep.
You face the same issues however you do it. It's a physical thing you have to do. And there's some software that does it now to a greater or lesser extent. And the intent is to integrate however that works, whether it's the software itself or the way it works, into something in the low end of what we're put together. So that at the high end, you have a straightforward and consistent interface, and you specialize out the lower end by federating out to things that already exist, building things that work. In the example you described, you're using OpenStack as the basis for your management controller, as I understand it. You're not exposing OpenStack to the end users of the system. Right? They use it
not yet.
kind of inadvertently.
So I think we do like the idea of being able to treat a supercomputer a bit more like a cloud and make it a bit more self-service. But at the moment, we're very much in the it's a management controller. We don't expose that.
Trojan horse then, get some experience in this context and then.
Exactly. Yeah. Once you've got the system and the API set up, then you can expose them to whatever or whoever you choose, right?
When do you think you might have users actually using this in the real world?
So we've got some systems which are managed by OpenStack at the moment. So the analytics platform that you saw earlier, Eureka, that uses OpenStack, along with the huge stack of software you saw on the right. The login systems that Doug talked about, already managed by OpenStack in a few deployments, and all of the deployments from this point will be managed via OpenStack.
But you don't have it running in HPC environments
No.
just yet?
No.
So when do you think you might have it running in HPC environments?
Well,
I think you might have it mature enough to be able to do that.
there's the question.
HPC environments, it's just not handling the HPC workload. Yeah. So it's handling things which are configuration.
So we've got two lines of compute product. There's the XC, which is the real sort of top end, and then there's the CS line, which is more of a cluster product. We are planning to support the cluster product first, which can scale to thousands of nodes. Clearly, we're not going to do that on day one, but I think that's within the next year. The top end, not sure at the moment. It's sufficiently far away that I can't give you a decent date.
Last
What?
question, I guess. Have you logged any of this? Have you pasted any of the code that you're using or the methods that you're using online?
We haven't really. Yeah, I think to this point we've been a bit more. We've been fairly insular. Doug mentioned that we've made various bits of code available. We have contributed some of our work back, but there's a decent chunk of it that we haven't so far. And it's a good point. Perhaps the first step on that road is the ideas, and then let the community decide what is the right content to.
I think a lot of people would be interested in this. I think it's an area that in order to start operating at scale, we need to get a handle on, and it would be really good for people to start putting stuff on it so that you can build a community around the testing of infrastructure. de-risk deployments and spare that. That would be really helpful.
It's a good idea. Yep. Thanks. I think it looks like that was the last one, so we'll call it a day. Thanks, everyone.
Thank you.